So we've gone over refraction and what refraction is, and when light moves from any wave, when any wave goes from one medium to another and changes speed, the direction of the actual wave itself changes. Usually, when we're talking about refraction, we only tend to look at light waves, but it does actually happen with all waves. And when you get to A level, this is important because you start to look at ultrasound, and some people get confused here because they hadn't realised that they had assumed that refraction is only something that happens with light, but it happens with all waves. So, let's say originally we said that when light goes from a more dense to a less dense material, it moves towards the normal, and when it goes from a more dense to let me just make sure I said that the way around. When it goes from a less dense to a more dense medium, it moves towards normal. When it goes from a more dense to a less dense medium, it moves away from the normal. And that's where you can have total internal reflection coming out from, say, water to air or glass to air or anything from more dense to less dense. So we've gone over that anyway. Now, the relationship with all types of refraction is this. We can work it all out using Snell's law. So different materials have different what we call refractive indices or refractive. They have a different refractive index. And it's basically a measure of as to how much the material will slow down light. So basically, you can have. Hang on a second. So the relationship between and this is specific to light at the moment, but it can be applied. Like the symbols are specific to light, but it can be applied to all waves. So the refractive index can be defined as the speed of light in a vacuum divided by the speed of light in that particular medium. Now, so the speed of light in a vacuum is obviously c. So c divided by c will give 1. So the refractive index of a vacuum is 1. And something like air is very close to the speed of light in a vacuum. And so the refractive index is going to be very close to 1. But it is slightly slower than it would be in a vacuum. So the way that we can work out these things is if we're going, let's say, from glass to air or from air to glass, we can work out we can work out the either the angular incidence or the angular refraction, depending on what they give us, based on this formula here, and you can rearrange it. You can also look at the relationship using this one here. So V1 over V2 is equal to sine theta over sine theta 2, sine theta 1 over sine theta 2. In this case, theta 1 is the same as angle of incidence, theta 2 is the same as angle of refraction. And that is also equal to the second refractive index over the first refractive index. So the task is to use this simulator that we've got up here to see if you can find out the refractive index of glass and the refractive index of water. And the way to do that is by setting one of the materials as air and one of them as water, and then repeat the process for one of them for air and one of them for glass. You can do it coming out of air or coming out of water or going into water. It doesn't really make any difference. The same you can still calculate the answer. So the task is to work out the refractive index of the refractive index of water and the refractive index of glass. Okay,